Let's dive right into one of the biggest mysteries in all of science. What is dark matter? I mean, it's 85% of all the stuff in the universe, but we know next to nothing about it. But what if a really fascinating new idea is telling us we've been looking at it all wrong? You know, for years, the picture we've all had in our heads is that dark matter is just one type of particle, kind of slow, kind of boring, and it barely interacts with anything. But what if that whole concept, the one you read about everywhere, is just completely outdated? And, this isn't some fringe idea. Some of the biggest names in physics, like Lisa Randall at Harvard, are saying, hang on a second. It seems really strange to think that our part of the universe is this incredibly rich, complex zoo of particles and forces, while the dark part is just one thing. They think it's way more likely that dark matter is a whole complex world of its own. So, thinking like that really cracks the door open for a much more exciting and, frankly, radical theory. It was first put out there way back in 2005 by a researcher named J. Alfred, and it's called the dark plasma hypothesis. Alfred's big idea was this. What if a huge chunk of dark matter isn't a solid or a liquid or a gas? What if it's actually the fourth state of matter, a plasma? But, and this is the key, not our kind of plasma. We're talking about a plasma made of totally new, exotic particles that aren't the stuff we're made of. So, how in the world did he come up with that? Well, it wasn't just a wild guess. Alfred built his case on what physicists call self-interacting dark matter, and he laid out 5 key clues that all point in the same direction. Let's walk through them. Okay, so you can think of these 5 things almost like ingredients in a recipe. You take a really weak electric charge, you throw in a bunch of neutral particles, you add in super low density, maybe turn up the heat, and mix in some indirect plasma effects. When you put it all together, you get a situation where it's almost impossible for dark matter to form atoms. Instead, it stays a plasma. So first up is this idea of a dark electric charge. The theory goes that some dark matter particles might have their own version of an electric charge, but it's incredibly weak, like 1/100th or even 1/1,000,000th of the strength of the charge we're used to. It's just way too feeble to pull particles together and hold them in a stable atom. But here's the part that'll blow your mind. Even if it's 1,000,000 times weaker than our electromagnetism, this dark force is still 10 to the power of 30 times stronger than gravity. So it's weak by our standards, but in the grand scheme of cosmic forces, it's an absolute giant compared to gravity. Okay, the second clue is what's called the neutral particle buffer. Researchers figure that for every one charged dark matter particle, there are maybe 5 or 6 neutral ones hanging around. These neutral guys act like a screen or a buffer, getting in the way and insulating the charged particles from each other, which weakens their already faint electric fields even more. Third is just a simple matter of space. Dark matter is spread out incredibly thin. The distances between individual particles are so vast that they hardly ever physically bump into each other. So how do they interact? Through long-range forces, their weak electric fields. And you know what? That kind of long-distance interaction, instead of direct collisions, is one of the textbook definitions of a plasma. Clue number 4. The dark universe might just be hotter than ours. And that's totally allowed by the standard model of cosmology. If it's hotter, the dark matter particles have more energy. They're zipping around faster, which makes it even easier for them to escape those weak binding forces. They just have too much energy to settle down and form atoms. And the 5th clue, well, this one is the real kicker. You can call it the 1% rule. Here's the thing. Dark matter doesn't even have to be fully turned into a plasma. It turns out that in plasma physics, if you just ionize as little as 1% of a gas, the friction and interaction between those few charged particles and all the neutral ones is enough to make the entire cloud act like a plasma. Okay, so now that we've laid out the case, it is so important to be really clear about what we mean by dark plasma, and maybe even more importantly, what we don't mean. So let's get this straight. Dark plasma is made of new, exotic dark matter particles, and they're interacting through their own unique dark forces. This is absolutely not just regular, ordinary plasma that's too cold or dim for us to see. That idea has actually been ruled out. If it were ordinary stuff, it would have messed with the afterglow of the Big Bang, the cosmic microwave background, in a way we just don't see. And what's so cool is that J. Alfred's hypothesis from 2005 wasn't just a flash in the pan. He was way ahead of his time. And now, years later, a whole body of research is starting to echo what he first proposed.
I mean, you can literally watch the idea catch on. Alfred is in 2005. Just 3 years later, you have Sean Carroll and his team saying, hey, maybe dark matter really is a plasma. Fast forward to 2015, and other physicists are arguing that plasma physics should be the starting point for this whole investigation. By 2016, you have more researchers proposing that dark matter inside galaxies is a dark plasma. It's a real convergence of ideas from separate teams.
This quote from Heikenheimo's team really just nails it. It captures the whole shift in thinking. The problem is no longer just find one weird particle. The problem is now understand an entire invisible ecosystem. And the main tool you're going to need to do that is plasma physics. So what's the big takeaway from all of this? It's that our whole picture of that invisible 85% of the universe is changing, and changing fast. We're moving away from the idea of some simple, boring substance. It's looking more and more like a huge part of it is a dynamic, complex, self-interacting plasma with its own set of rules. And that leaves us with one last really provocative question to chew on. If dark matter isn't just a particle, but a whole plasma with its own version of electromagnetism, what other crazy complex structures could it be forming out there in the dark? What other cosmic dramas are playing out completely hidden from our view? It changes everything.